successful software grows, and of course that means also our test suites keep growing the longer we keep maintaining our software. And we have a lot of customers where a few years ago they used to have test suites that ran for a few minutes or maybe a few hours, and nowadays their test suites run for days or maybe even weeks, and that is painfully slow. If you have the same problems, you are in good company. These are the logos of the companies that registered for the workshop until last week. And as you can see, these companies are from very different domains. They don't have the same way of developing software, and they all use different technologies. So this is not a problem that is specific to one domain or a technology, but rather it goes across all of this. And we see the same thing with our existing customers. But there are some simple ideas how we can improve the situation. When our tests are starting to be too long to execute in a reasonably short time, one very simple idea is to not rerun all of our tests whenever we make a change to the software system, but rather to select a small subset of our large test suite and run that much more frequently. Of course, that idea only works if that small subset of tests has a very high probability of finding new bugs. And we present today two approaches how that can be done that have a little bit of a different cost-benefit ratio. The first one is test impact analysis, which I will talk about in the first part of the workshop. And then in the second part of the workshop, my colleague Raphael will talk about Pareto testing. Then we'll have a short demo, so you can see what this looks like in our tool Teamscale and how it feels to work with these analyses. And then in the final part, I'll present a case study that we did with one of our customers, Bayerische Versorgungskammer. They are a big insurance company here in Germany. And we'll show you there how they evaluated both of these analyses and what the result was and how they're using them today. All right, before we go into the nitty-gritty, I want to show you a little bit about our company because I don't know how well you know us yet. We are CQSE. We are originally a spin-off of TU Munich over 10 years ago. Our founder founded the company, but nowadays we are distributed over all of Germany. And we also, since a few years ago, have an office in Sunnyvale in California, where we can be closer to our customers in the Silicon Valley. We are at the moment 57 full-time employees, 53 of which are have studied computer science. And most of us have done some research or a PhD in software quality, and that is our main focus. And we developed the tool Teamscale, and two of the analyses that Teamscale can do, we will show today. So let's get into it. The problem that we face is that our test suites take very long to run. And usually we have already exhausted all the options that we have to easily solve this problem, because some ideas when you have a long running test suite are, can we just parallelize this to make it faster and just run it on 50 virtual machines in parallel or something like that. But even with that approach, we usually quickly get to a certain limit where it's not cost effective to just throw more money and more machines at the problem. This is especially true for a lot of our customers where they don't have a nice test pyramid that looks like this, where you have a lot of unit tests that are quick and cheap and easy to run in the bottom, and a few select end-to-end tests at the bottom, but rather usually our customers have more like the ice cream cone of death, where you have a few unit tests and very, very many end-to-end tests at the top. And these are usually much, much harder to run in parallel and to make faster. We also have some customers that have an even bigger problem because they don't only deal in software, they also deal in hardware. And you can see an example here from one of our customers, BMW, where we did a big study on this machine here, which is a test machine. And this runs, I think, 12 parallel versions of the same hardware chip, and they run 12 tests at all times against this chip. And when they want to run all of their test suite, which is 10,000 tests, then if this machine runs 24 hours straight without a pause, it takes them over 2 weeks to run all the tests. And that is, of course, painfully slow, because if I, as a developer, check something into the code base, then I don't want to wait 2 weeks until I get feedback on whether I broke something. By then, I've probably already forgotten the details of what I did in the code change. Plus, it's usually not really clear which code change actually caused the tests to fail. So we're not only looking to debug one test failure that is clearly correlated to a certain code change, that is usually easy, but rather we see 50 test failures that are related to 200 code changes. And you first have to find out which code change actually caused which test failures. So because the feedback cycle here is so slow, we are getting very inefficient and we are losing a lot of time just tracking down the source of the bugs that we introduce. Now, there is a very simple idea how we can make this faster. And to show you how that works, I first have to introduce to you a visualization that we use. This is a so-called tree map. In this tree map, every rectangle represents a component of a software system. And the more lines of code there are in the component, the bigger the rectangle is. So this over here is a large component. Here we have a few small ones. What I'm going to do now is I'm going to zoom into these components. First, I'm going to show you all the classes that are in each component. So every rectangle now is a class. And then I'm going to zoom in one more step and show you all the methods that are in the classes. And again, the more lines of code are in a method, the more the bigger the rectangle is. And this is actually our own code. So this is the code of Teamscale, our system that analyzes software. And what I'm going to show here is one code change that we did, where we implemented support for Java closures in Teamscale. Teamscale is a source code analysis program, so we need to understand the source code that you have, and one of the languages that we support is Java. And so when Java received closures as a language feature, we had to implement support in our parsers and scanners and so on, and in our analyses for closures. And the code change looked like this. Gray means that these methods were not changed. Everything that is colored has been changed to implement this new feature. And orange here means the method already existed before we made the code change, and we just made some changes in there. The red parts mean that we have added a completely new method to the system. And what I'm going to do now is I'm going to run our whole test suite. That's a few thousand test cases. And of course, we're not going to run them in real time, then we'll be sitting here for a while, but rather we'll run them a bit accelerated. And every time a test runs, we will see the coverage it generates in white. You already see a few white specks over here. So this is the first test that runs in a test suite, and the methods that it covers go white. And then in the next frame, they will become green, and the next test is in white. And then so we can see how the green coverage is building up over time. So I'll start it now. And you can see that the tests are running over the system. Some areas are getting tested more frequently than others, and some areas are not getting tested at all. But the most important realization that we have here is that almost none of the tests run through the code changes that we made, which isn't very surprising because when we first implemented support for Java in Teamscale, no one knew that Java would be getting closures, and no one was writing tests in advance that would be testing that functionality. That doesn't really make sense. And so it's no surprise that when we implement a new feature, it's rather unlikely that most of our tests will actually be able to find a bug in the code changes that we made, because they simply don't run through them. And this observation is what we can use to speed up our test suites. And this is what test impact analysis does. We can simply only select the tests for our small test suite that we want to run more frequently that actually run through the code changes that we make, because these tests are the only ones that are actually able to find new bugs. If the tests that we have run through only unchanged code, then they can't behave differently than the last time we ran them. So if they didn't find a bug last time, they won't find a bug this time. How does this work? Each rectangle here represents one test case. Green is the coverage that they generate. They all have slightly different coverage. When we know which test case runs through which code, then we can now know when we make a code change, which test cases actually run through the changed code areas. We can use this to, in the first step, to select only the test cases that run through the changed code and throw away the rest. And this leaves us with usually a much smaller set of tests. Sometimes, of course, it can happen that we change some very central functionality in the system. Like, for example, you have a web application and every test as the first step has to do a login. Then when we change something about the login, of course, all tests will be selected here. So as a second step, we do another optimization, which is we prioritize the test. Because not all of these tests will in the end have a failure. Most of them will probably be successful. So ideally, what we'd like to do is we'd like to reorder the tests so that ones that are likely to fail are ordered first. And of course, if we could do this perfectly, it would be great, and we wouldn't have to run tests at all. We would just know which ones fail. So this is not how it works in practice. But we've tried a lot of different heuristics for how we can order and prioritize these tests. And we found one that has an above average chance of selecting the tests first that have a good, that will likely fail. And the heuristic here is that for every second of test execution time, we select that test which produces the most additional coverage. So we've already covered a few methods with the test that we've executed, and then we select the next test that will produce the most additional coverage in the time that it has. And with that heuristic, what we can achieve is usually a picture like this, where we have the failing test cases rather early. And this is great because at this point here, when we have the first failing test case, we already have a signal that the software version that we have contains a bug, and that we need to go back to development. The developers can already start debugging. And we also know that we don't have to ship this version of the software into later, more expensive test stages, like a manual test, for example. It makes more sense to first fix the bugs and rerun our smaller test set again to make sure that it passes the first quick check, so to speak. Now, with this approach, we can select a smaller test suite and run that much more frequently. And the big question for us was, how effective is this? How effective is this actually? Because it could be that in the most common cases, we have to select so many tests that in the end, it doesn't save us much time, and then it wouldn't be worth the effort to implement this. So what we did was a lot of studies with both open source systems and real industry systems, where we collected a lot of data about historic bugs, and to try to see if we use this approach, how much time can we save and how many of the bugs do we find in the time that we spent on testing. And since real bugs are few and far between, one wouldn't always think so if you're working on a real software system, but there's not enough to do a real large-scale study. We also employed a second approach called mutation testing, where we purposefully inject bugs into a software system and then try to see if our test suite finds it, both the whole test suite and our subset that we have selected. And these two approaches combined are really great because with the mutation testing, we can do like hundreds of thousands of bugs and get a lot of data. And with the industry systems, we can verify that the results that we get from mutation testing are actually representative of what we find in practice. And luckily for us, the results actually matched. What we saw with both approaches was that if we spend 1% of the time that it takes to run all the tests, on average, we find 80% of the bugs that the whole test suite would find. So this is a really big saving. If we are rather generous and spend even 1% extra, then we can even find 90% of the bugs that the whole test suite would find. So this is a really big reduction in runtime, and we still can find most of the bugs. So this enables us to give feedback much more frequently, find most of the bugs much earlier, and we don't lose anything because we can still rerun the whole test suite in the usual intervals that we have, like once a day, once a week, once a month, whatever works for the size of the test suite that we have. So all the bugs that we didn't find here, we can just find later on. how does this work? How do we get all the data, and how does the analysis work? How is it implemented? To be able to do this analysis, we need to know which test case runs through which method. This is called test-wide coverage. And to get this test-wide coverage, what we have to do is continuously, we have to execute all the tests. So for example, if your test suite takes 2 weeks to run, then we would probably do this once a month. If your test suite still runs over the weekend, then we can do it once a week, whatever works for the test suite that you have. But in that interval, we run all the tests, and for every test we record with a so-called coverage profiler through which code does it run, and then we get this test-wise coverage. This data we send to Teamscale. Teamscale stores this and historizes this, and then when we do code changes, we run our CI pipeline, and the CI pipeline knows which commits were added, which code changes happened, and sends this information to Teamscale. And Teamscale uses this test-wise coverage information that it has to do the test selection and the test prioritization, and outputs an ordered list of impacted tests. And then our CI pipeline takes those tests and has the job of instructing the test runner to only run those tests instead of rerunning all the tests. All right. Setting up all of this, so making sure that we continuously report this test coverage and integrating it into the CI pipeline, so the CI pipeline talks to Teamscale and so on, this is usually a bit of an effort. And also for some customers that have especially large test suites, you also run into some problems with the amount of data that is generated here, because this test-wise coverage over here, this can get rather large. We have some customers where one run of all the tests produces 10 gigabytes of test-wise coverage data. So you also have to be careful how you manage that. And of course, the bigger your software system gets and the more tests you add, the more of a pain it is to manage all that data and make sure the CI pipeline works correctly and so on. So usually there needs to be someone who keeps their thumb on this topic and makes sure that all of these things keep working, because we are tightly integrated here in the CI pipeline, and if this doesn't work, then of course the developers notice, and we don't want that. So because we saw that to implement this is quite a bit of effort, we were asking ourselves, isn't there maybe a simpler option how we can achieve something similar with maybe a little longer runtime, but still a big speed up that is a lot easier to set up and to maintain. And that is how we came up with the idea of Pareto testing that Raphael will show now. But before we go into this, now would be a good time if you have any questions about test impact analysis. All right, then I hand over to you, Raphael.
Yep, I just took over the screen. Can you quickly confirm?
Yep.
Okay, great. All right, as Fabian already mentioned, we were looking for a simpler option because, yeah, test impact analysis is quite a bit of effort to set up. And the idea was to spend a bit more time, get maybe slightly worse results, but save on effort on setup and on maintenance. And our basic idea was was to not look at the changes and instead use the redundancy that is often present in big, historically grown, long-running test suites. And I would like to show you an example to make this a bit more tangible. Again, we have this visualization of tests that Fabian already presented. And the core idea now is of this approach is that usually one fault does not cause one test failure, but rather multiple. So when we have a fault represented by the color of these bugs here in our code, then this usually causes more than one test to fail. In this case, for example, the orange one here causes these 2 to fail, the blue one causes these 4 to fail, and the purple one only this single bug only causes the single test to fail. And what we want to do now is, instead of trying to find every single test that fails, we try to find one representative of each. So it's usually enough if a developer has one failing test, so he can fix the fault behind it. And what we try to do is, in as little time as possible, find as many of these representatives as possible. And to go a bit more into detail on why there is potential for optimization here and how we can optimize for finding this one representative, I would like to show you another example with a paint program. This is called Pixelator. It's an open source Java software, and we chose an image editing software, not because that's what all of you are building frequently, but rather it's something that everyone is familiar with and probably has used at some point in their lives. And this one here is maybe somewhere between MS Paint and Photoshop in terms of complexity and its capabilities. And we visualize it here again with the tree map, as Fabian already explained. Here we are again at the very high level of packages, and then we add some more detail and include the classes here, and finally down to the method level. So these are all the methods in Pixelator. And what we now do is we color them according to whether they have been run in Pixelator's test suite. So everything that's green here has been, all the methods that are green here have been run through at some point in Pixelator's test suite. We have method coverage here. This means we don't know exactly which lines have been run or if the method has been executed completely or only part of it. But we found that for this type of analysis, that's completely enough, and adding more detail would only decrease performance without significant benefits. We didn't just record this coverage in total, but as before, test by test. So we can split it up here, and this is now the test suite you saw aggregated before in the individual test. And while you can't see much detail here anymore, I guess you can still roughly see that tests that are close to each other often have fairly similar coverage, while tests that are far away from each other have fairly different coverage. And this idea I want to go into a bit more. How does the execution order actually influence test coverage? Because what typically happens in a test suite is that we execute it package by package. And when we order a test suite in different ways, we can achieve different things. So and achieve different coverage. Let's take a look at the normal execution order of the Pixelator test suite here. The first test we run is called test Gaussian blur. So some type of filter that can be applied to images. And everything that's green here, again, is all the coverage that this single test adds. Now we add another test, and we have colored in blue everything that has already been tested by or already been covered by the first test. So only what's green here is actually additional coverage. All the other parts have been run through already by previous tests. Then on the next test, we can see we have even less green. And if we take a look at the name, we can see that it's fairly similar to what we had before. Again, another one of these blur filters. So this also implies that the functionality is pretty similar, and we can also see that the coverage is pretty similar. And for the last test, we'll look at in detail test smart blur. We can see we only have very little additional functionality that is being tested here. And this is also what we mean with redundance. So the tests almost only test what has already been covered by previous ones. And what we actually know from studies is that often either all tests find a fault that run through code or none of them do. So what we can do here is we can achieve a good cost to benefit ratio if we executed only one of these blur filter tests and exclude the others if we want to optimize for time. Of course, to find every single fault, it would still be good to run all of them. The consequence of this, we visualize here in this chart. On the x-axis here, we have from 0 to 100% of the runtime of the whole test suite. And on the y-axis, from 0 to 100% of the coverage of the whole test suite. And if we add the coverage over time here, we can see that it's sometimes slightly above, sometimes slightly below, but roughly linear in its execution. And what we did then was to modify the order to improve this, how quickly we gain coverage. And we use a heuristic for this that's very similar to what we already had in Fabian's part with the additional coverage per time. So we look at which test adds the most additional coverage every second for us in a single second of testing time. So the first test that is selected with this is this test create and modify selection. Very different from what we had before. And now the interesting part, let's look at the second test. We can see we have way less blue relative to the overall coverage. We still have some. This is very typical for end-to-end tests because they just cover some of the same code. If you have the whole application running, you're always going to get some overlap with your tests. And if we look at the name, we can also see that it's a very different area that this test is running in. So it's not like we had before with the different blur filters, but here we actually are testing completely different functionality. And again, here we see a lot more green. And with the last one, number 4, we also add 4 tests here. Previously, we only had maybe 3 or 4 additional methods tested with the fourth one. Here we can still see at least half of it is additional coverage, and while also the amount of previously covered methods is increasing. Now let's add this to the graph we've seen before. This was the previous coverage, and now here is the coverage with the optimized order. And we can see this already looks a lot better. So yeah, here we have each test as a data point. And if we now draw a line at around 10% of the runtime, we can see that we have about 3 times as much coverage. So we have chances to find faults in 3 times as much area of the code as we had before. And this is what we're optimizing for here, to get good coverage of the whole system and to have a quick test suite that we can run often. And we also evaluated this with artificial faults that Fabian mentioned before, with mutation testing, and also real historical faults in industry systems. And what we found here is we were definitely worse than with the test impact analysis, which was expected. We need about 6% of the total runtime to get 80% of the faults, and about 11% of the total runtime to get up to 90%. As mentioned, this is not quite as good as the test impact analysis, which is fairly unsurprising since we use less input data, we update the data less often, but it's also a lot easier to set up. Just quickly again here, we have the whole setup for the test impact analysis. And the crucial part is that we need to actually integrate into the CI pipeline. And for every single test run, we need to calculate this new set of tests to run. While with the Pareto optimization, all you do is you calculate a set, maybe once a month, for example, and then can add it statically to your CI pipeline, and then have one short set of tests that you run maybe after every commit, and one long set of tests that's your whole test suite that you run maybe on the weekend, for example, or overnight. So what we've presented now are 2 techniques to find a lot of faults in a very short amount of time. They come with different costs and provide different benefits. And while with the test impact analysis, we only needed 2% of the time to find 90% of the bugs. With Pareto optimization, we needed some more time, 11% of the time to find the same amount of bugs. Test impact analysis requires some more effort in setup. We need to have this deep integration into the CI. And with Pareto optimization, we only need to record coverage once, for example, per month or even per quarter. We would say that these are both valid in terms of their cost to performance ratio, and we also have customers using both. It really depends on how much effort or how much time you spend on testing, how much effort you're willing to put into this type of analysis, and also how easy it is to integrate, so the whole system environment, which one makes more sense. Okay, this is the theoretical part. We would now go into a short demo. In the meantime, are there any questions?
No questions in the chat.
All right. Okay, then I would go along with the demo. The demo we are doing is we are testing Teamscale itself. So we are testing Teamscale and using the analysis of Teamscale. And for a bit better understanding, I'll just give some background first before we jump into the tool. This is how our tests look like. We have this type of test pyramid where the highest number of tests is at the bottom, and then it gets less and less the higher we go up in abstraction level. So the quite a lot of unit tests with almost or over 7,000. And then the UI tests are the least, but a very typical picture also, they actually take the most amount of time. And that's also why these are the ones we will look at. So we will run some UI tests for Teamscale with the test impact analysis. And the scenario we are looking at is we had to implement a feature. We have these external credentials in Teamscale. So these are your data. These are for connecting to external systems, like, for example, some Git or GitLab, GitHub, or also some maybe Azure DevOps or Jira. Whichever system Teamscale connects to, the connection so username and password and so on are stored here. And the functionality that was missing here is that we can actually delete them. So far we could only edit them and maybe change the permissions, but we couldn't remove them. So what we did was we implemented that. And now we want to test it to make sure that everything still works. And also, of course, the new feature works. Now let's take a look into Teamscale. All right, we are first taking a quick look at the tool itself. I will just log in here. And what you can see here in Teamscale is this is the activity perspective. It shows the commit stream along with some other information, like, for example, test coverage uploads. So this is already an upload of test coverage. Just for your understanding, Teamscale is made up of these perspectives that you can see in the sidebar here, and each of them delivers a different view on the software quality data that Teamscale has. As I said, we already made the initial upload of test coverage. We can take a quick look at this. We again have these tree maps here where we can see where all of our tests ran through in green, and the gray areas where the tests did not run through. And we also have already made our changes here, and that's what we want to test. So this last commit we just made, and we want to test it now. So normally, of course, this would run in your CI pipeline in whichever continuous integration environment you're using. For the purposes of this demo, I'm just doing this manually and running our Gradle tests or our Gradle setup here by hand. Yeah, this will now perform all the tasks necessary, and then like building Teamscale and so on, and then run the tests. It's already starting the UI test server. In the meantime, we can take a quick look at some background on this ticket we implemented. So this is the issue that we implemented here, enabled deleting account credentials. And in Teamscale, we can then see some additional information. Oh, now the test server is coming online. And tests are running through. This test automation here is Selenium, so it's basically just automatically clicking through my browser here and performing these tests. We can also see we are somewhere in external credentials here and doing some stuff there. So it seems we are in the right area. And yeah, we will just quickly wait this out. Shouldn't take long. Okay, looks like it's done. All right, we can see of our several hundred tests, only these 5 have been run. Four of them, just some background info, 1 of them has been an edit test. 4 of them were actually impacted tests, which we can also see here. So here we could see which tests have been affected by these code changes that we made for this ticket. And we can also see that 1 of them failed. So what we would do now normally is, of course, search for the bug and try to fix it as quick as possible. And in this case, the fix is already prepared, and I will just apply it, and then immediately also run the continuous integration again to make sure that my tests are running again. And again, Teamscale will automatically select only the tests that are relevant. Now, in Teamscale, I can also see the changes that are being made. So here's now the analysis for the latest change. And we already get it. Teamscale does incremental analysis, which means it's only looking at the changes that were made in the last commit. So this is basically our commit here, and we can look at it in detail. Also for this, we can take a look at the impacted tests. These will be the tests that are run by the CI pipeline, so it will only be this one test. There it goes. All right, then. So it should be the can delete external credentials. And this has been run here, can delete external credentials. It has passed. So with this CI being done, I'm now done with my feature. I have implemented it, and it could be merged from the testing side. All right, this was a very brief demo for the test impact analysis. We saw that the tests were running quite quickly, and there were only very few tests selected for a very small feature like this. I also want to quickly show you the Pareto analysis. We have all the data we need for it, since it's also this test-wise coverage data that we use in the test impact analysis as well. So we can look here in the Pareto ranking view, and then it immediately shows us a graph that looks like what we had on the slides as well. So we see this total runtime on the x-axis and the coverage on the y-axis. And then we can basically select here with this slider how many tests we want to execute. And we can see at the bottom that the tests are getting less if we reduce the time here. And now we only have these few tests. And we can then download this list as a CSV, or we can also get them via the API. And then we can run only the subset of tests and integrate them into the CI pipeline for quicker testing. All right, so far for a very quick demo in Teamscale. Did any questions come up during that?
There are no questions in the chat.
All right. Then for a quick summary, with the regular CI, the UI tests alone would have run over 30 minutes. So we would still be sitting here and running UI tests. With the test impact analysis, we had this very short test runtime of only maybe a minute. And then we could already look at the failing test, attempt the bug fix. This was now a bit quicker than it would have been in real life, of course. But yeah, then we could even rerun the tests and be done with all of this in less time than it would have normally taken to only run the UI tests once. All right, that would be the practical demo part. Then I would give over to Fabian again for a case study that we did with a customer.
All right, thanks. So what I want to show you in the last part of the workshop is what we did with our customer Bayerische Versorgungskammer. They are a big German insurance company. They do insurance for a lot of different types of jobs, like, for example, orchestras and free, what's they called in English? Free artists, sorry, and similar jobs. And they are a really old insurance company. They've been around for over 100 years. What we looked at with them is one of their big internal business systems that is written in Java. They have a lot of tests there as well. When we first talked to them, they were barely able to run the tests every night. So the test took around 12 hours. So if you start early in the evening, you're done late in the morning, and then people can get feedback on their code changes on the next day. But obviously, this is already on the border of painful, and they expected to be adding more tests in the future. So at some point, it wouldn't even be possible to get all of this done in one night. And so they were very interested to find out whether Pareto testing or test impact analysis could help them with that.
We still see the summary slide.
I know. Okay. That should be me. Now you see a different one.
Thanks.
I just wanted to get those points off before I switch here. But thanks for double checking. So what we did with them is what we call a pilot project. And in a pilot project, we want to find out basically which of these two analyses has the better cost-benefit ratio for the concrete software project that we're analyzing. Because this will be different depending on how you test and how many tests you have and how big the pain is for you and how redundant your tests are. And what we do in this project is we have a kickoff where we get everybody on board so everybody knows what is going to happen. And then we record test-wise coverage for the tests that the customer has. But we don't do this for the tests that they have today, but rather we do this for the tests that they had like a year ago. And why do we do this? It's much easier and much cheaper to do this type of evaluation by looking at historic data. Because then we don't have to integrate in the current CI and we don't have to possibly interrupt the developers and ask people to do a lot of work in the CI pipeline, but rather we can do everything offline and we can just see what would test impact analysis and Pareto testing have done for us in the past year. We have all the code changes and we can record test-wise coverage for the state of the software a year ago. And then from that, we can see what the impact of these analyses would have been and conclude from that if it's worthwhile to implement one of them or maybe even both of them for that software system. And this allows us to make the decision which analysis is more interesting with as little cost as possible, because we don't want to invest a lot in both analyses and then later on decide we're only going to use one of them, obviously. So once we have that data, that historic data, we do a little bit of validation to make sure that the data is actually correct and we're seeing all of the software system that we want to analyze and not missing anything. And then we do this retrospective evaluation to see which of the analysis produces which results. We presented that to BVK, and then afterwards they decided to use some of these results, and we of course also helped them roll it out to a few more projects. And I'm going to go a bit more into detail how that worked for them and what the results were. But before we do that, I want to give you one more idea of how this test-wise coverage recording actually works. So just to recap, Pareto testing, we only need the test-wise coverage, and then we get a list of selected and prioritized test cases. For test impact analysis, we also need to look at the code changes. And for the test-wise coverage, what we do is basically when you run your application and then you perform tests on it, it doesn't really matter if these are automated tests or if it's someone manually clicking through the UI, or if this is API tests, or if it is maybe even tests like unit tests or integration tests that run in the CI pipeline. It always works the same way. What we do is we install a so-called test-wise coverage profiler. And maybe you also already know coverage profiling from your CI pipeline, where you maybe already do it for your unit tests. It's roughly the same principle. This is the tool that interacts with your application while it's running and can deduce which lines of code are being executed while the application is running. And this is also why it doesn't really matter if this is a manual test or an automated test. We just monitor the application as it's running, and whether it's a user typing something into a text field, or whether it's automation or a unit test that causes code to be executed, the profiler always knows what the application is doing. And with this, we can write a so-called coverage report, which is just a text file that tells us, okay, line 5 and 6 were executed, but line 7 was not executed. But this is not enough. This only lets us record coverage for the whole test suite. So if we ran 15 tests, then we know all of the 15 tests combined ran through these lines. But what we need to know is test-wise coverage. So which test runs through which methods and lines. And to get this, we need one more piece of information, which is when do tests start and when do they end. And this usually comes out of either an automated process for your automated tests, where the test runner knows, okay, now I'm starting test 1, then it can send this information to the profiler. And now I'm done with test 1 and starting test 2, and it sends another signal to the profiler. But it also works for manual tests, where then the manual tester just has to click a button to say, okay, now I'm done with my current test, I'm starting a new test. Then the profiler also knows which test is running through which code. And then what we get in the end, not just one coverage report, but one coverage report for every test that we have. This is what we call test-wise coverage. Of course, how these applications are instrumented and how this recording works in practice is very different for different technologies. So we have different tools for Java than we have for C++, and then we have for ABAP, for example. But the big picture always looks like this. When we have this data, what we do is we send it to Teamscale, and then Teamscale lets us play what if. So we can see what would the impact have been if we had these analyses in the last year, for example. Now, the first result that you get when you send this data to Teamscale is the test-wise coverage for every test. So in Teamscale, you can click on the test and you see this nice tree map and you see which code does this test case run through. You get this for every test case. But as a side result, you of course also get to know for all of the test suites that you measured what the overall coverage for that suite is. And this is usually already also an interesting result, because many of our customers only measure test coverage for the unit tests, but they have a lot more tests in the higher test stages, like integration test, system test, automated UI test, and so on, but they don't know anything about the coverage yet. So this was the same for BVK. They only knew the coverage of the unit test, but not for the higher test suites that we looked at, which were these two here. One of them is normal business test cases, and the other one are chain tests, which means that a lot of business cases are run in a series, one builds on the results of the other. But as you can see, both of these test suites have roughly the same coverage. There's not much difference here. So this was already interesting for the customer, but of course, this was not the main thing that we were after. What we were really trying to find out is how much test time could they expect to save if they had used the test impact analysis and the Pareto testing in that time frame. And how do we evaluate this? Let's first look at test impact analysis. What we can do is, for every day in that year, we know exactly what the developers checked into the version control system. These are the code changes that happen on that day. And based on those code changes, we can ask Teamscale to use the test-wise coverage to give us a list of impacted tests, as we've seen in the demo. And then we know the cumulative runtime of those tests, because we measure that as well when we measure the test-wise coverage. And so we know how long it would have taken to execute these impacted tests on that day. And then we can do this for all the 365 days that we have in that time frame. And of course, sometimes it will be less, sometimes it will be more. And we can always compare it to the total runtime of all tests, because this is what BVK was doing at the time when we did the study. Every day they rerun all of the tests. So this was a good way to see how much they would have saved. And now the result that we got when we did this looked like this. In red, you can still see the 12 hours that they usually take. In blue, you see how much time it would have taken on the specific day to run the impacted tests. And the first thing that made me very happy when I saw this graph for the first time was when you just draw the line at 50% of the usual test time, you see that very, very few days take longer than that. So there's already probably a very huge saving in there. But to get a bit of a clearer picture of how much that is in practice, actually, we took the same data and reordered it into a so-called histogram. Here, every bar represents one bucket of testing time. So all the tests all the days where the tests took less than 20 minutes are in the first bucket. The ones where it took 20 to 40 minutes are in the second bucket, and so on. And you can see that most of the interesting stuff happens here in very low test times compared to the 12 hours that they usually have. And to put it into very clear numbers, on 93% of all days, the test runtime would have been less than 17%. And this is already a pretty good result. Now, we did the same thing for Pareto testing. So we looked at we plotted the same graph that you saw on the demo that you also saw on the slides before. And as you can see, this one is actually a bit steeper than the ones that we had in the studies that we did, which is because there is quite a lot of redundancy between the tests that they have on these high test stages. And for them, with just 1 hour of test runtime, they already get over 99% of method coverage. So that is also a very good result. Of course, it could be that with these tests, we always select tests in the static list that have nothing to do with the code changes that we make. That is one risk with Pareto testing. So we wanted to know if that actually could happen in practice. So we compared the result from the Pareto list with the result from the test impact analysis to see if the impacted tests are also represented in the Pareto list on most days. And what we found is on those 365 days, on all days, at least one of the impacted tests was in the Pareto test list. So there's no day where we only select tests that have nothing to do with our code changes. And on average, it was 17% of impacted tests in there. So we have a good chance of finding bugs with the Pareto list as well, with the code changes that were made there. So how could they be using those analyses? Because they were by that point convinced that it was a good idea to use one of these analyses, but they wanted to know what it would actually look like in practice if they implemented it. And what they do right now is what we call rerun all. So every night they build a software system, which takes, I don't know, maybe an hour, and then they run all of their tests for 12 hours. With the test impact analysis, what they could be doing instead is what we call time boxing. This is what we suggested to them, which means that during the day, when they normally don't run any tests, they now take 2-hour slots, 1 hour to build a software system, 1 hour to run impacted tests. And of course, in some of these slots, there will be very little to do because the code changes don't cause many impacted tests. In some other slots, maybe they modified some central class, then a lot of tests will be impacted, and then we won't be able to run all of the impacted tests in that slot, but we'll have the next slot. If that is not full, then we can run some of them there. But so every developer checking something in has at least a certain chance to get their code changes tested and get feedback within 2 hours. Of course, we've seen in the histogram that this should work out very well because most of the time the code changes for a whole day will not be able to fill that time slot. So the code changes of the last 2 hours probably won't either. So we'll have a lot of slots that are not totally full. What they would still be doing in that scenario is to do the rerun all in a regular interval, so nightly as long as it's possible. For once, to make sure that if we fill all of the slots in the day, that we can still run all of the remaining impacted tests and catch all of the bugs, and also to update the test impact data in a regular interval, as we've shown before. So they would still be doing the same thing they are doing now. So they don't lose anything, but they really gain a good chance of getting feedback much, much earlier during the day for the developers. This was test impact analysis. How would it look like with Pareto testing? Rather similar. So they would also be doing time boxing, but instead of running tests that depend on what was changed before, they just rerun the Pareto list every time, 1 hour of tests. That still gives them a good chance to find bugs, because as we've seen, there's usually some tests in there that run through the code changes, and the ones, the bugs that we don't find here, they still also catch at night when they do the rerun. Once a month, or maybe in even longer intervals, they will update the Pareto test list to make sure it keeps up with the latest code changes. Now, what did they do in the end? Because Pareto testing had such good results for them with very high coverage values for very little time investment, they decided to go with the cheaper option, so to speak, because it takes less effort to implement it, because that was good enough for them. So we actually implemented Pareto testing here, and they have been using it for a while now, not only for this project, but we also implemented it for a few other projects that worked rather similar. So it was also really easy for them to roll it out to more people and get even more out of the analysis. Now, after they've used it for a while, we wanted to know how effective was it in practice for them. So we looked into the data again about, I'd say 6 months after they started using it. And we found that we find 70% of the failing commits in only 5% of the test run already during the day. And these 70% of failing commits, they would have previously only found the next day. So this is quite the speed up that they get out of this. So far for this case study. Any questions about this? Or maybe if you have questions about the earlier parts, you can also feel free to also ask them again.
There are no questions in the chat.
All right. Then that concludes our workshop. We will be here even after the workshop finishes. So if you have some questions that you'd rather ask one-on-one, feel free to stay on. If you're going into your well-deserved evening, then I wish you a nice evening, and I hope to see you soon again. If you found this interesting and would like to let other people in your team know about it, we can also repeat this workshop for free for you and your colleagues. In those sessions, we can also go into more detail about your particular situation, your problems, your technologies, and so on, and answer all the questions that you have. So feel free to contact us about that. Before you leave, a few more things. We will be having a few other events in 2023 that we'd be happy if you also join. One is a software intelligence talk by Salzgitter Digital Solutions. They're a big steel mill, and they'll talk about how they moved their software development from dusty to modern. That will be on January 18th. And we'll also have a workshop about another test analysis called test gap analysis that helps you find untested code changes before you release them to production, where they usually cause production defects. So if you're interested in that, feel free to pre-register. We'll be announcing the dates shortly when this happens. So thanks again. We will start a short feedback form now. We'd be very happy if you take the time to make the 2 clicks to let us know how we did. And if you have the time for the longer feedback form, that opens when you leave the meeting. Have a nice evening. And if you want to ask some one-on-one questions, feel free to stay on now.